Touching one phase of a delta distribution line while touching the ground presents a significant electrical shock hazard. In a delta system, the voltage between any two phases is the line voltage. If the system is ungrounded, there isn't a direct path for current to flow back to the source through the ground. However, stray capacitance and leakage currents can create a path, potentially delivering a shock. If the delta system is corner grounded, one of the phase conductors is connected to ground. Touching any other phase conductor while grounded would create a phase to ground fault, resulting in a substantial current flow through the body and a severe shock. The severity depends on the system voltage, the grounding impedance, and the body's resistance. Without knowing the voltage of the system, it is impossible to know the magnitude of the voltage potential. Touching one phase of a Y distribution line while touching the ground also poses a substantial electrical shock hazard. In a Y system, the voltage between a phase conductor and the neutral point is the phase voltage. Typically, the neutral point of a Y system is grounded. If one touches a phase conductor while grounded, current will flow from the phase conductor through the body to the ground and back to the neutral point at the source. This completes the circuit, causing an electrical shock. The magnitude of the current depends on the phase voltage, the grounding impedance, and the body's resistance. Because the neutral is grounded, this fault is likely to cause a large current flow. Similar to the delta system, it is impossible to know the voltage potential without knowing the voltage of the system. To elaborate further, consider a typical scenario with a 120/208 volts Y system. The voltage from any phase to ground, which is the neutral, is 120 volts. If someone touches one of these phases with bare feet on the ground, they are exposed to 120 volts. The current flow through the body depends on the body's resistance, which can vary significantly depending on whether the skin is wet or dry. Wet skin significantly reduces resistance, allowing more current to flow. Even a small current in the milliamp range can be dangerous and cause muscle contractions, making it difficult to let go. High currents can cause ventricular fibrillation, leading to cardiac arrest. Now consider a delta system. If the delta system is ungrounded, touching a single phase might not immediately result in a large current flow. However, this situation is deceptive. An ungrounded system can still develop a voltage potential to ground due to capacitive coupling and other factors. If a second fault occurs on another phase, a direct phase-to-phase fault through ground is established, resulting in a very high current flow. The ungrounded delta system is therefore often considered more dangerous because it gives a false sense of security. If the delta system is corner grounded and one touches a phase other than the grounded phase, the full phase-to-phase voltage is impressed across the body to ground, as if it was a single phase to ground, resulting in a hazardous situation. In both delta and Y systems, the presence of a ground fault circuit interrupter, or GFCI, can significantly improve safety. A GFCI detects small imbalances in current between the hot and neutral conductors, indicating a leakage to ground. When such a leakage is detected, the GFCI quickly interrupts the circuit, minimizing the duration of the shock and reducing the risk of serious injury. GFCIs are commonly used in residential and commercial settings, particularly in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Electrical safety practices should always be followed when working with or around electrical systems. Firstly, always assume that any electrical circuit is energized until proven otherwise using appropriate testing equipment. Secondly, use personal protective equipment, including insulated gloves and footwear, when working with electrical circuits. Thirdly, never work on electrical equipment while standing in water or on a wet surface. Fourthly, ensure that all electrical equipment is properly grounded. Fifthly, use ground fault circuit interrupters in areas where there is a risk of electrical shock. Sixthly, follow lockout/tagout procedures to de-energize equipment before performing maintenance or repairs. Seventhly, if unsure about any aspect of electrical work, consult a qualified electrician. Eighthly, regularly inspect electrical cords and equipment for damage. Ninthly, never overload electrical circuits or extension cords. Tenthly, be aware of the location of electrical panels and emergency shut-off switches. Additional considerations include the importance of proper grounding and bonding. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices, such as circuit breakers and fuses, to quickly clear the fault. Bonding ensures that all metallic parts of an electrical system are at the same potential, minimizing the risk of electric shock. Regular inspections and maintenance of grounding and bonding systems are essential to ensure their continued effectiveness. Furthermore, it is important to understand the role of impedance in limiting fault current. Impedance is the opposition to the flow of alternating current and is composed of resistance and reactance. Higher impedance in the fault path will reduce the magnitude of the fault current, reducing the risk of damage to equipment and injury to personnel. Impedance can be intentionally added to the grounding system to limit fault current, but this must be carefully engineered to ensure that the system remains safe and effective. Electrical safety standards and regulations, such as those established by the National Electrical Code, or NEC, provide detailed requirements for the safe installation and operation of electrical systems. These standards are constantly updated to reflect new technologies and best practices. It is essential for electricians and other electrical workers to stay up to date on the latest requirements to ensure that they are following safe work practices. NEC Table 310.15b16 provides ampacity ratings for conductors based on insulation type and temperature rating. NEC Section 250 provides requirements for grounding and bonding. NEC Section 408 covers switchboards and panel boards. The severity of an electrical shock depends on several factors, including the magnitude of the current, the duration of the shock, the path of the current through the body, and the frequency of the current. Alternating current, or AC, is generally more dangerous than direct current, or DC, at the same voltage and current levels because AC can cause sustained muscle contractions, making it difficult to let go. The path of the current through the body is also critical. Current that passes through the heart or brain is more likely to cause serious injury or death. In summary, both delta and Y distribution systems present electrical shock hazards when one touches a phase wire while grounded. Y systems with grounded neutrals typically provide a more direct path for fault current, while ungrounded delta systems can create a false sense of security. Proper grounding, bonding, the use of GFCIs, and adherence to electrical safety practices are essential to minimize the risk of electrical shock in both types of systems. Knowledge of the specific voltage and grounding configuration is critical for assessing the potential hazards and implementing appropriate safety measures.